So the external direct product of the two groups how to define அப்படின்னு பார்த்தீங்கன்னா that is A and B or B groups. Define the A cross B is defined as the collection of the order pairs, that is the A comma B. A is belongs to A and B is belongs to B, and this is called the external direct product of the groups. The component multiplication is defined as A1 B1 and A2 B2 is A1 A2 comma B1 B2, and then this is a group. G is a group with identity EA comma EB. EA is the identity element for A and EB is the identity element of B. A inverse and B inverse, this is the element of corresponding A capital A and capital B. And internal structure pathina, this is the internal structure of the A cross B. The closure of A is defined as A comma EB. A belongs to A. The closure of B is defined as A comma B, that is the B belongs to B. Then the closure of A, the structure, the closure of A is isomorphic to A, and the closure of B is isomorphic to B. And both closure of A, closure of B is a normal subgroup of G, normal subgroup of G, and G is equivalent to the closure of A and closure of B. Okay, these are very important point. And every G equal to A comma B, for every element of the G as a unique decomposition, G equal to AB with A belongs to A bar and B belongs to B bar. And the closure of A intersection, that is a bar intersection B bar, is equivalent to EA comma EB. At least this is the identity element corresponding to G. And generalization to the n group, already ரெண்டு குரூப்புக்கு பார்த்தோம். இது ஜெனரலைஸ் பண்ணீங்கன்னா n குரூப்புக்கு ஜெனரலைஸ் பண்ணும்போது we can define like this: G1 class, G2 class, and so on Gn. The collection of G1 G2 Gn, Gi is belongs to Gi with the component multiplication. The identity and inverse, this is the identity and this is the inverse. So A cross B க்கு போட்டது G1 G2 Gn க்கு define பண்றோம். That's all idea. And the same way G1 bar define பண்ணலாம். G1 bar is defined as E1 E2 Ei minus 1 Gi Ei plus 1 Ei. So then Gi bar is isomorphic to Gi. Gi bar is a normal subgroup of G, and G equal to the product of G1 G2 Gn, that is G1 bar G2 bar Gn bar. So every G has a unique decomposition like that: G equal to G1 G2 Gn. Gi is belongs to Gi bar. So then Gi bar intersection G1 bar and so on Gn minus 1 bar, Gi plus 1 bar, Gn bar, this is the identity element. Okay, this is the idea based on this result. And internal direct product particular group G is the internal direct product of a subgroup H1 H2 Hn if each Hi should be the normal subgroup of G, and G equal to H1 H2 Hn, G equal to express the product of H1 H2 Hn, and Hi is the intersection with H1 H2 Hi minus 1 Hi plus 1 Hn, that is equivalent to identity element. So G is isomorphic to H1 cross H2 cross Hn. This is the internal direct product. So the proper definition of the internal direct product: so G be the group and N1 N2 Nn the normal subgroup of G, then such that G is the product of N1 N2 Nn, these are normal subgroup, and given G belongs to G, that is the element of G is expressed as uniquely expressed as G equal to M1 M2 Mn. Each Mi is belongs to Ni. So G is called the internal direct product of this N1 N2 Nn. N1 N2 Nn is the normal subgroup. And a finite abelian group, so that means G be the finite abelian group of order of G, that is the product of prime factors, that is p1 power a1, p2 power a2, and so on pk power ak, with a distinct primes pi. So capital P1, capital P2, capital Pk be the silo pk group, the pi group, pi subgroup, and so then the each pi, each silo p group, pi group is normal subgroup to G, and G is expressed as the product of silo p subgroups, and this is called every G belongs to G as uniquely decomposition, like that G equal to m1, m2, mk, with each mi belongs to pi. Then G is the internal direct product of p1, p2, pk. So this is example for the G is the finite abelian group of order of G, and isomorphic to the external direct product. So G is the internal direct product of n1, n2, nn, internal direct product of n1, n2, nn. So G is isomorphic to, that is n1 cross n2 cross nn. That is when you define the function from the Cartesian product of n1 and nn, this is to G, that is pi of n1, n2, nn equal to n1 into n2 into nn. This is an isomorphism. This is an isomorphism. And G is the internal direct product of the normal subgroup n1, n2, nn. So then for this is one of the result for I is not equal to J, for the distinct ni and nj, the intersection is identity element, ni intersection nj is identity element. If A belongs to ni, B belongs to nj, and I is not equal to J, then AB equal to BA. Okay. So result of that is this our result. So in the case of the K1, K2, in the case of if K1, K2, Kn is the normal subgroup of G, with G equal to the product of K1, K2, Kn, with each intersection K intersection Kj is equal to identity element, for the I is not equal to J, that is a distinct intersection of the Ki and Kj. It doesn't imply that G is the internal direct product of Ki. So the internal direct product that is satisfy this condition. In the condition satisfied, that is called the no need, it is the internal direct product of the Ki. So, and another result G be the group, and suppose that G is the internal direct product of n1, n2, nn, and let T equal to n1 cross n2 cross and so on nn, then G and T are isomorphic. So G and T are isomorphic. So G into the group, G into the internal direct product of n1, n2, nn, and T equal to, when you define the product of n1, n2, nn, then G and T are isomorphic. And here define the some mapping, that is the psi from T to G, that is psi of B1, B2, Bn is the product of something. No need proof. That is A and B are groups, then A cross B, A and B are groups, then A cross B is isomorphic to B cross A. Okay, this is the one of the result. We can prove easily this is the A cross B is isomorphic, that is homomorphism proof pannu, and 1-to-1 onto proof pannina, that is both are isomorphic. The case of the A and B are groups. The same way G1, G2, G3 are groups. G1, G2, G3 are groups. Then G1 cross G2 cross G3 is isomorphic to G1 cross G2 cross G3. You more simple proof pannala when you define the function like that. Psi of G1, G2, comma G3 equal to G1, G2, G3. We can prove easily this is the isomorphic. So just to homomorphism proof panna, and then 1-to-1 onto proof panna, both are isomorphic. This generalize pannalam. Generalization like this is also isomorphic. Here T equal to the product of G1, G2, Gn. Then for each I equal to 1 to n, there is a homomorphism pi I of T. There is a homomorphism pi I of T on to Gi. Then the kernel of pi I. Then the kernel of pi I how to define, that is the kernel of pi I is defined as the collection of the elements G1, G2, Gn belongs to T. That pi I of the G1, G2, Gn is equal to identity element. This is the kernel of pi I definition. That is the EI is the identity element in the GI. So the ith component of this is the ith component, that is this is exactly the set of elements where the ith component is EI and the other components are arbitrary. So the kernel of pi I is defined as the G1 cross G2 cross Gi minus 1 cross EI cross Gi plus 1 and Gn. So this kernel is isomorphic to the direct product of all groups except Gi. Direct product of all groups except Gi. Okay, this is maybe important point. And GBA group, let T equal to, let GBA group, let T equal to G cross G. Then D is defined as the collection of G comma G, which is belongs to G cross G. That is for every G belongs to G, is a group. This is a group. This D is a group that is isomorphic to G. That is isomorphic to G. And it's a very simple result. And another result, D is a normal. This collection D is normal in T if only if G is abelian. This is maybe important. Okay. So the normal Fruppona, that is the D is normal in T, that is D is normal in T, that is G is abelian. That means when you choose for any element G comma G belongs to G, for A comma B belongs to T, just we want try to prove that is D is normal in D is normal in T, G is abelian Fruppona. Normally in T means A comma B, G comma G, A comma B whole inverse. நம்ம இதுவரை போடுறது single element இருக்கும், இங்க order pair இருக்கு, that's all idea. But the structure the same structure da. So A comma B, G comma G, the A comma B whole inverse we can express A inverse comma B inverse. That is when you multiply it, already multiplication define பண்ணிருக்கிறோம். So AG A inverse, BG A inverse, that is belongs to D. So that means this element is in D, because of this the structure. So its two components are equal, that is AG A inverse equal to BG B inverse for every A, B, G belongs to G. Therefore when you take that B equal to C, when you take B equal to C, then AG A inverse is equivalent to EG E inverse equal to, that is identity element, that is EG E inverse, that is equal to G. So that this is simply AG A inverse equal to G, that is AG equal to G in vandrum for A comma G belongs to G. Therefore from this G is abelian. Like that we can prove the converse part, that is normal subgroup in the case of G is abelian. So when you define the D like that, when you define the like that, D equal to the collection of G comma G belongs to G cross G. The T is G cross G, Cartesian product of the G cross G. G into the group. G comma G, that is the collection of G comma G is called the D. For the element of G, it is a group, that D is a group that is isomorphic to G. And then this is a normal subgroup. Okay, if and only if G is abelian. The D is normal subgroup if and only if G is abelian. Normal subgroup in T. So மறந்துடுச்சுனால நீங்க இதெல்லாம் ப்ரூவ் பண்ண ட்ரை பண்ணலாம். Okay, so it's a very simple idea. and G be a finite abelian group, and G is isomorphic to the G into the finite abelian group. G is isomorphic to the direct product of its silo subgroup, that is silo P group, direct product of silo subgroup. So G is a finite and abelian, finite subgroup, finite abelian group. So G is finite and abelian. So fundamental theorem of finite abelian group, G is isomorphic to direct product of cyclic groups of prime powers. So that is prime power orders, that is G is isomorphic to Z P1 power A1 cross G Z P2 power A2 cross into, that is Cartesian product of Z Pk power AK. Okay, that is the, so for the factors by prime factors, that is each prime P dividing the order of G, SP is the silo P subgroup of G, then SP is isomorphic to the product of ZPI power AA. Since G is abelian, all subgroups are normal. G is abelian, all subgroups are normal. So therefore silo subgroups are unique. Silo subgroups are unique. So the order of G should be is equivalent to product of order of SP. So SP intersection SQ, when you take the distinct silo P group and silo group, that is equivalent to identity element. So for the P is not equal to Q. Therefore the properties of the internal direct product, G is isomorphic to SP1 and SP2 and is an SPM. This is the idea. So the P1, P2, PM are distinct primes, that is dividing order of G. So G is a finite abelian group, that is we can express G is a finite abelian group, that is we can express the direct product of that is G is isomorphic to the direct product of its silo subgroup. Okay, it's maybe very important result. So maximum group theory பொறுத்த மட்டும் காலேஜ் டிஆர்பியில் டைரெக்டாக ரிசல்ட்டாக தான் கேட்க முடியும். ரொம்ப காம்ப்ளிகேட்டட் லைக் தட் CSIR நெட்டில் கேட்குற மாதிரி கொஞ்சம் ட்விஸ்ட் பண்ணலாம் கேட்க மாட்டாங்க, டைரக்ட் கொஸ்டினாக தான் கேட்பாங்க. ஸோ A and B are cyclic subgroup. A and B are cyclic groups of order M and N respectively. So then the Cartesian product of A cross B is cyclic if and only if M and N are relatively prime. M and N are relatively prime. So that means ஸோ கொஞ்சம் ட்ரை பண்ணுங்கள் how to prove அப்படின்றது ஞாபகம் வச்சுக்கிறது ஈஸியாக இருக்கும். Suppose A and B are cyclic group, that is generated by some element, that is called the A, that is A is generated by A, B is generated by B, and the order of A is M and the order of B equal to N, that is given. So G3 of M comma N equal to 1. Suppose G3 of that is relatively prime M and N are relative prime, that is consider the element A comma B is belongs to A cross B. So that is we want to try to prove this is the cyclic. The A cross B is cyclic. So order is its order. What is the order of this one? Is the LCM of M comma N. G3 of M comma N equal to 1. What about the LCM of M comma N? That is the product Mn. Okay, this is obviously true. So A comma B as order வந்து Mn. A comma B ன்றதனுடைய order வந்து Mn. Which is the order of the A cross B? A cross B. Am I correct? So what is the conclusion? A comma B is the order Mn, that is the order of the A cross B. That is A cross B is cyclic. Therefore the A cross B is cyclic, that is generated by the some element A comma B. Because of the order of A is M, order of that is A is generated by A, that the element order is M, that element order is N, therefore A cross B is cyclic. In the case of A cross B is cyclic, we want to try to prove the M and N are relatively prime. So that means cyclic means that is generated by some element, that is A comma B. So the order of A comma B is mn. The order of A comma B is also the LCM of m and n. So LCM of m and n is mn. So LCM of mn is defined as the related to with GCD. So LCM into GCD equal to the product of the two element. It's a very simple result. So LCM of m comma n equal to mn divided by GCD of m comma n. So this is mn divided by GCD equal to mn. So GCD is already, which is implies GCD equal to GCD of m comma n equal to 1. What is the conclusion? The m and n are relatively prime. M and n are relatively prime. So that is also very important result. Okay, the Chinese remainder theorem, that is m and n are if m and n are relatively prime integers, u and v are any integers, so we can find the integer x such that x is congruent to u mod m, x is congruent to v mod n. Okay, so when you use that, that is since m and n are relatively prime, GCD of m comma n equal to 1, the group Zm and class Zn is cyclic of order mn, that is isomorphic to Zmn. That is isomorphic to Zmn. When you define the homomorphism, consider the homomorphism pi from Z to Zm cross Zn. When you define the function pi of x equal to x mod m and x mod n, so the kernel of pi is mz intersection nz, that is the LCM of m comma n z, that is mn z, and the m and n are relatively prime, that is GCD of m comma n equal to 1. The pi induces the isomorphism, that is Zmn to Zm cross Zn. So therefore that means for any u comma v belongs to Zm cross Zn, there exists the unique x mod mn such that pi of x equal to x mod m x mod n, that is u comma v. Therefore there exists the integer x, the modulo mn, satisfying the x is congruent to u mod m and x is congruent to v mod n. Okay, this is the idea. And the example of a group G and normal subgroup n1 n2 n1 n2 nn such that G is a product of n1 n2 nn, and intersection of ni intersection nj is the identity element for the distinct ij, that G is not internal direct product of n1 n2 nn, internal direct product of n1 n2 nn. So this example is the Kellen 4 group, that is v equal to e a b a b, which is abelian. The n1 is e comma a and n2 is e comma a, n2 is e comma b, n3 is e comma ab. This is a G equal to n1 n2 n3. We can write intersection of these two is identity element only, but G is not an internal direct product of n1 n2 n3 because of internal direct product records the subgroup commute element wise, that the representation be unique, that is n1 n2 n3 are not all normal. So actually V is abelian. Actually since V is abelian, all subgroups are normal. So therefore this is the condition, internal direct product is stronger, therefore the G is equal to, we need the G equal to n1 cross n2 cross n3, that is implies more order of G is equal to order of n1 order of n2, that is 8, but order of V into the 4 da. So it is impossible, therefore this is another that is satisfying that condition, but it is not a direct product of corresponding n1 n2 n3. And another alternatively G equal to S3, that is a symmetric group for symmetric group on 3 letters. So here n1 equal to a3 and n2 equal to e comma 1 2. So then G equal to n1 n2 and n1 intersection n2 equal to e, but n2 is not normal in S3, but a3 is normal. Okay, doesn't satisfy the hypothesis that all ni are normals. Okay, and better example, G equal to z2 cross z2. So n1 equal to 1 comma 0, that is n2 equal to 0 comma 1, n3 equal to 1 comma 1. This is G equal to n1 n2 n3, and intersection of ni intersection nj is the only identity element 0 comma 0. But G is not an internal direct product of n1 n2 n3, because of the direct product would require the G is isomorphic to n1 n2 n3, which has order 8. So but order of G equal to 4 only, so that is not unique. Therefore example 1 comma 1 can be written as 1 comma 0 and 0 comma 1, or 1 comma 1 itself, or 1 comma 1 itself. Okay, this is the good example for the CSIR net helpful இருக்கும்னு நினைக்கிறேன். Okay, maybe TRB கூட இது மாதிரி கேட்கலாம், கொஞ்சம் காம்ப்ளிகேட்டடா. So G is the internal direct product of the normal subgroup. Internal direct product of normal subgroup n1, n2, nn, if only if G equal to n1, n2, nn, and ni intersection n1, n2, ni minus 1, and so ni plus 1, nn, this is equal to identity element. So in the case of G is the internal direct product of normal subgroup if only if this is the condition. And another one, G be the group and K1, K2, Kn or normal subgroup of G. Suppose the K1 intersection K2 intersection Kn equal to identity element. When you define Vi is the quotient group G by Ki, Ki normal subgroup, and then there is an isomorphism of G into V1 cross V2 cross and so on Vn. Okay, these are results. Results the maximum direct கேட்பாங்க. So K1, K2 normal subgroup இருக்கும்போது அதனுடைய intersection should be identity element இருக்கும்போது, when you define the quotient group G by Ki, so that is there is an isomorphism of G that is into V1 cross V2 cross Vn, that is the quotient group isomorphism இருக்கும். Okay, well, that is there exists an isomorphism of G that is isomorphic to V1 cross V2 cross Vn. So it's a and another one, G be a finite abelian group such that it contains a subgroup H0 is not equal to E, which lies in every subgroup H is not equal to E. Okay, that is G must be cyclic, then G must be cyclic. So G into the finite abelian group, that is it contains a subgroup non-identity, that is H0 is not equal to E, not only the identity element, that is the proper subgroup. So then which lies in the every subgroup H is not equal to E, then G must be cyclic. G must be cyclic. So G is here. How to define the order of G? Order of G is the prime power n for some prime P. And G be a finite abelian group, and G is isomorphic to a subgroup of a direct product of finite number of finite cyclic group. Okay, where G is a finite abelian group, then G is isomorphic to the subgroup of the direct product of finite number of finite cyclic group. This is another result. Finite non-abelian group. Given example of the finite non-abelian group G, which contains the subgroup H0 is not equal to E, such that H0 is the subset of H for all group H is not equal to E of the G. The example is quaternion group. Quaternion group of order 8. H0 is minus 1 comma 1 is the center of the quaternion group. As of order 2, the every non-trivial subgroup Q8 of Q8 contains the H0. Am I correct? Every non-trivial subgroup of Q8 contains the H0. The subgroup of Q8 is of the form it is generated by I and J and K and minus 1. All non-trivial subgroup contains the minus 1 comma 1. So H0 is contained in every non-trivial subgroup of Q8. So the Q8 is non-abelian. Q8 is non-abelian. Okay. And every group of order P square, P is a prime, is either cyclic or isomorphic. So every group of order P square, P is a prime number, there is either cyclic or is isomorphic to the direct product of two cyclic groups each of order p, so G be the group of order p square. The center of G is a non-trivial subgroup, that is, since G is a p group and as of order p or p square, center of G as is a non-trivial subgroup, that is the order வந்து p or p square, because of the order of G is p square, that is should divide by the order of Z of G, that's nothing but the p or p square. Suppose in the case of order of Z of G equal to p square, then G is abelian. Obviously G is abelian. That is a very important result. Then the fundamental theorem of finite abelian group, G is either cyclic or isomorphic to ZP cross ZP. ZP cross ZP. G is either cyclic or isomorphic to ZP cross ZP. So that is the proof, I thought. And in the case of order of Z of G equal to P, then the quotient of the G by Z of G as order வந்து P, so P square by P, that is the P. Hence the order of some group is P, then it is called the cyclic, so but then G is abelian. So well known fact, G by Z of G is cyclic, then G is abelian. So that is contradicts to order of Z of G equal to P, that is therefore order of Z of G cannot be P, so therefore order of Z of G should be equal to P square and G is abelian. So G is either cyclic, therefore G is either cyclic or ZP cross ZP. Okay, it's also very important one. So G is A cross A, that is G equal to A cross A, where A is cyclic of order P, P is a prime number. So then how many number of automorphism does G have? That is இது ஒரு ரொம்ப important result for the competitive examination. That is G is A cross A ன்னு கொடுத்துட்டாங்க, where A is cyclic of order P ன்னு கொடுத்துருக்காங்க. So G is isomorphic to ZP cross ZP, which is a vector space of dimension 2 over the field FP. That is the automorphism of G or exactly the invertible linear transformation of this vector space. That is the number of automorphism is equal to number of invertible 2 by 2 matrices over FP. That is the general linear group of order 2, the corresponding to the entries in the P, that is the prime numbers, that is ZP. So that is general linear group order, already we know that P square minus 1 into P square minus P. Okay, that is a P minus 1 whole square and P into P plus 1. Okay. So the number of automorphism is P square minus 1, P square minus P. And another one, K1 cross G equal to K1 cross K2 cross and so on Kn. Describe the center of G in terms of those of the Ki, in terms of describe the center of G in terms of those of the Ki. That is center of G is denoted as Z of G. Z of G is Z of K1, Z of cross Z of K2, Z of Kn. So that K1, K2, Kn is belongs to G is in Z of G. That is the if and only if it commutes with every element of G, that is for all G x1, x2, xn belongs to G. This is K1, K2, Kn into x1, x2, xn. This is x1, x2, xn, K1, K2, Kn. This holds if and only if Ki xi equal to xi Ki for every xi belongs to K for all ai. So that is for the Ki belongs to Z of Ki for each I. The Z of G we can express like this. Okay, like for the collection of K1, K2, Kn, that is Ki belongs to Z of Ki. So that is, we can express the product of direct product of z of k1, z of k2, z of kn. Same way, G equal to, when you express the direct product of k1, k2, kn, and G belongs to G, the n of G we can express the collection of elements in the G, that is n tuples, and that is satisfy the condition, that is xg equal to gx, that is normalized group. And G is a finite group n1, n2, nn or normal subgroup of G such that G equal to n1, n2, nn. Okay, and order of G equal to order of n1, order of n2, order of nn. Then G is the direct product of n1, n2, nn. Then G is the direct product of n1, n2, nn. Okay. And this is the fundamental theorem of finite abelian group. Every finite abelian group is the direct product of cyclic group. Every finite abelian group is the direct product of the cyclic group. That is a very important one. Okay, this is maybe direct question. And definition of invariance. That is, G is a abelian group of order p power n. P is a prime number, and G equal to the product of direct product of a1, a2, ak. Each ai is cyclic of order p power ni. N1 with n1 greater than n2 and so on, n greater than equal to nk greater than 0. Then the integer n1, n2, nk are called the invariant of G. So to define the invariant, that is for abelian group of order prime power. So then G equal to the direct product of a1, a2, ak. That is G is the direct product of the cyclic group of order p power ni with the condition n1 greater than equal to something. That n1, n2, nn, nk are called the invariant of G. And order of G and partition of n, that is order of G is defined as order of a1, order of a2, order of ak. That is a p power n1, p power n2, p power nk. That is the p power n1 plus n2 plus nk. So order of G is a p power n, and n equal to should be equivalent to n1 plus n2 nk. So the invariants n1, n2, nk form a partition of n. The invariant is related to the partition of n. And the cyclic subgroup ai are not necessarily unique. That is, consider the Klein 4 group. Cyclic subgroup ai are not necessarily unique. That for example, consider the Klein 4 group G equal to E A B A B with the condition a square b square equal to b, a b equal to b a. So that is, then G is the direct product of a and b. That is the generated by a, that is generated by b. The a b are cyclic group of order 2. So then G equal to AB cross B, that is AB is a cyclic group, is also cyclic group of order 2. So the decomposition is not unique. That is, the decomposition is not unique. Therefore, the multiset order, that is 2, 2 is fixed. That is. And G is an abelian group. S is any integer, then G of S is defined as the collection of x comma G, x power S equal to E. And G is since G is abelian, G of S is a subgroup of S. G of S is a subgroup of S. And if G and G dash are isomorphic abelian group, then for every integer S, G of S and G dash of S both are isomorphic. This is the GBF abelian group of order p power n. GBA abelian group of order p power n, and p is a prime number, g is the direct product of a1, a2, ak, ai is the generated by some element ai is cyclic of order p power ni. This is the n1 greater than equal to n2 and so on greater than equal to nk greater than 0. M is any integer, that is ni nt greater than m greater than equal to nt plus 1. So then g of p power m is equal to b1 cross b2 cross bt at plus 1 like this. The bi is generated by a p power ni minus 1 is this cyclic of order p power m. The order of g power pm is p power u, that is u is defined like that. Okay, a very complicated result. G is defined like that. Then order of g power p, g of p is p power k. This is one of the result, very important one. Two abelian groups of order p power n are isomorphic if only if they have the same invariant. This is the if and only if condition. So we can prove same invariant in which, that is we can prove that are isomorphic. There are a number of non-isomorphic. This is a very important. CSIR NET la use பண்ற மாதிரி வரும். Number of non-isomorphic abelian groups of order p power n is equals the number of partition of n. Okay. So this is a very important result for any competitive examination. Number of non-isomorphic abelian group கண்டுபிடிக்கணும். Just try to find out the partition of n in the case of the prime power p power n இருந்ததுனா. So this is the there are the 5 non-isomorphic abelian group of order p power 4. This is the example. This is a good one, the corollary. There is a number of non-isomorphic abelian group of order n, that is p1 power a1, p2 power a2, pr power ar. Pi is a prime distinct primes. So number of non-isomorphic abelian group கண்டுபிடிக்கணும், that is partition p of a1, p of a2, p of ar கண்டுபிடிச்சினா போதும். That is the partition of a, that is ai. Okay, that is equivalent to the number of non-isomorphic abelian groups. For example, n equal to 2 power 3 square into 5, that is the order. So then the number of partition of 3 is p of 3, that is equal to 3. We will know that 3, 2 plus 1, 1 plus 1, 1. And number of partition of p of 2 is 2, 2 plus 1, 1. The number of partition of 1 is 1. So number of non-isomorphic abelian group of order 2 cube 3 square, that is 9 5s are 45 into 8. 8 5s are 40, that is the 32, 36, 360. Of order 30 is 360. What is the number of non-isomorphic abelian group of order 360 is 3 into 2 into 1 because of the partition of 3, the partition of 3, partition of 2 and partition of 1. This is equivalent to number of non-isomorphic abelian group of order 360. Like that, இது மாதிரி ஒன்றா ப்ராப்ளம் கேட்கலாம், CSIR நெட்லேயே கேட்டிருக்காங்க. So and otherwise direct result தான் கேட்பாங்க. So G is an abelian group of order p power n. P is a prime number. N1 greater than equal to N2 greater than equal to Nk greater than 0 are invariants of G, or the invariant of G. Therefore, the maximal order of any element in G is p power n1. Okay, maximal order of any element in G is p power n1. In the case of or invariant இருந்ததுனா, that is the n1 greater than equal to n2 or invariant of G. So then maximal order of any element of G should be p power n1. So that is a simple proof. The G is abelian. Fundamental theorem of finite abelian group என்ன சொல்லுதுனா, G is isomorphic to Z p power n1, Z p power n2, Z p power nk. G equal to the element is of the form a1, a2, ak belongs to G, ai belongs to Z of Z p power ni. The order of G is the least common multiple of orders of ai. So since each ai has the order dividing by p power ni, அப்படின்னா that is n1 greater than equal to ni ன்னு எடுத்துக்கலாம். For all I, the maximum possible order is p power n1. So this is the a1, that is the k1, a1 to be the generator of z of p power n1, that is a equal to 0 for I greater than 1. So the maximal order is a p power n1. And another result பார்த்தீங்கன்னா, G is a group a1, a2 and so on ak. These are normal subgroup of G. The such that ai intersection a1, a2, ai minus 1 is equal to identity element E for all I. Then G is the direct product of a1, a2, ak if G equal to the product of a1, a2, ak. G is the direct product of a1, a2, ak if G equal to a1 into a2 into ak. The case of a1, a2 is the normal subgroup and the condition satisfy the ai intersection with a1, a2, a minus 1 equal to E இருந்ததுனா. So using if finite abelian group as a subgroup of order m, finite abelian group if a finite abelian group has a subgroup of order m and n, then it has the subgroup whose order is the least common multiple of LCM of m comma n, whose order is LCM of m comma n. This is also like that. So for the finite abelian group has a subgroup of order m and n, then it has the subgroup whose order is least common multiple of m and n. So this is the one of the example. All finite abelian group of order 2 power 6. Finite abelian group of order 2 power 6. So first of all, number of non-isomorphic abelian group of order 2 power 6 is equal to number of partition of 6, correct? Number of partition of 6 number of partition of 6 is equivalent to like this, 3 plus 2 plus 1. So this is the number of partition of 6. So what is the conclusion? 11 non-isomorphic abelian group of order 2 power 6. So how to express this one? Z2 power 6. This is correspond to 6 ன்னு எழுதுறது. இது வந்து this is correspond to 5 plus 1. Okay. Okay. The 6. This is 5 plus 1. This is a 4 plus 2. This is 4 plus 2 plus 2. This is 3 plus 3. So இதனுடைய corresponding இதுதான். So what are the non-isomorphic abelian group? These are non-isomorphic abelian group. இது மாதிரி like that சின்ன சின்ன ப்ராப்ளம்ஸ் கேட்கலாம், கேட்கறதுக்கு நிறைய வாய்ப்புகள் இருக்குது. ஸோ எத்தனை நான்-ஐசோமார்பிக் எபிலியன் குரூப் இருக்கும் அப்படின்றத கேட்கலாம், ஃபைனைட் எபிலியன் குரூப். ஸோ இது மாதிரி எக்ஸ்பிரஸ் பண்ணலாம். இதே மாதிரி 11 power 6. Since 11 is a prime, so 11 is a prime. The number of non-isomorphic abelian group of order 11 power 6 is the number of partition of 6. So partition of 6 into the 11, which is 11. So the group are exactly the same as the previous one, that is with base அங்கே வந்து 2 இருந்தது, இங்கே base வந்து 11 இருக்குது, அவ்வளோதான் difference. So இங்கே express பண்ணும்போது z 11 power 6, z 11 power 5 like this express பண்ணுவோம். By 7 power 5, 7 power 5 na number of partition of 5 கண்டுபிடிக்கணும். number of partition of 5 na this is the partition of 5. So மொத்தம் எத்தனை வருது? 1 2 3 4 5 6 7. So therefore 7 non-isomorphic abelian group for the 7 power 5 find பண்ணலாம். அது என்னன்றதை express பண்ணலாம். Like this, the product of 2 primes. This is the product of 2 prime powers. The number of abelian group of order 2 power 4. So number of partition of 4, which is 5. The number of number of abelian group of order 3 power 4 non-isomorphic. So that is also 5. Therefore, number of abelian group of order 2 power 4 and 3 power 4, 5 into 5. 5 into 5. So that is equal to 25. Each group is of the form G2 cross G3. G2 cross G3. G2 is a abelian group of order 2 power 4. G3 is a abelian group of order 3 power 4. The same way, all abelian group of order 2 power 3 and 3 power 4 and 5. So number of abelian group of order 2 power 3 is the number of partition of 3, which is 3. That is, this is the another abelian group of order 2q. Remember, number of abelian group of order 3 power 4, the number of partition of 4, which is 5. So already previous problem I explained பண்ணிருப்போம். So the number of abelian group of order 5, order 5 பார்த்தீங்கன்னா that is 5 power 1 ன்னு இருக்குங்க. So partition of 1, that is 1, only is at 5. So therefore the number of abelian group of order 2 power 3, 3 power 4, 5 is 3 into 5 into 1, that is equal to 15. So each group is of the form, how to express in the is G2 class, G3 class, G5. G2 is one of the 3 groups and one of the 3 groups of order 2 power 3. G3 is one of the 5 groups of order 3 power 4 and G5 is equivalent to Z5. G5 equivalent to Z5. So it's a very important simple problem. Okay. And G is a abelian group. G is an abelian group of order p power n with invariance n1 greater than equal to nk greater than 0. H is not equal to E is a subgroup of G. Then if H1 greater than equal to Hs greater than 0 or invariance of H, so then K greater than equal to S, then K greater than equal to S, and for each I, Hi less than or equal to Ni, Hi less than or equal to Ni, I equal to 1 to S. Okay, this is a G is an abelian group of order p power n with invariant n1 something. H is okay is the subgroup, that is a proper subgroup, and that is if H1 greater than equal to Hs or invariant of Hr இருந்ததுனா, then this is the idea. Okay. So G is an abelian group and G be the set of all homomorphism of G into the group of non-zero complex numbers under multiplication. Then the pi 1 pi 2 is belongs to G cap, then pi 1 pi 2 by pi 1 pi 2 of G, pi 1 of G, pi 2 of G for all G belongs to G. Then G cap is an abelian group under operation defined. So maybe leave it. ஸோ இன்றைக்கி எடுத்தது அந்த நான் ஐசோமார்பிக் எப்லியன் குரூப் கண்டுபிடிக்கிறது ரொம்ப இம்பார்ட்டண்ட். நாட் ஓன்லி டிஆர்பி எக்ஸாம், சிஎஸ்ஐஆர் நெட் எக்ஸாமுக்கும் அது ரொம்ப ரொம்ப இம்பார்ட்டண்ட் ரோல். This is a pi is belongs to G cap and G is a finite. Then pi of G is a root of unity for every G belongs to G. And G is a finite cyclic group and G cap is cyclic, so order of G cap equal to order of G. Hence G and G dash, G and G cap are isomorphic. And G1 G2 not equal, or in G is a finite abelian group. Then there is a function pi belongs to G cap with pi of G1 is not equal to pi of G2. The same way G is a finite abelian group and order of G equal to order of G cap. G is isomorphic to G cap. G is isomorphic to G cap. So and pi is not equal to 1, which is belongs to G cap. G is abelian group. Then summation of pi of G equal to 0 for every G belongs to G. Is okay. G is a finite abelian group and with elements A1, A2, An, then the product of A1, A2, An is an element whose square is the identity. The square is the identity element. So in the case of G is in that like that as no element of order 2 or more than one element of order 2, then prove that A1, A2, An equal to E. Then okay, stop here. This is called the Wilson's theorem. This P is a prime number, then P minus 1 factorial is congruent to minus 1 modulo P, minus 1 modulo P. This is maybe important. So this is P is an odd prime, and if 1 plus 1 by 2, 1 by 3 plus 1 by P minus 1 equal to A by B, A, B are integers, then P divides A, P divides A. If P greater than 3, then prove that is the P square divides A. So P is an odd prime and A is not equal to 0. P be an odd prime and A is not equal to 0 modulo P is said to be quadratic residue of P. Already discussed பண்ணிருக்கோம்னு நினைக்கிறேன். If there exists an integer x such that x square equal to A congruent to A mod P, x square congruent to A mod P, so that so there exists a x square, that is called the quadratic residue. So then the quadratic residue of P form a subgroup Q of the group of non-zero integers modulo P under multiplication. That type of quadratic residue of P form a subgroup of the group of non-zero integers modulo p under multiplication. This is maybe result. So we can define the quadratic, the subgroup G inradhu, that is ZP nu eduthakalam, that is a multiplicative group of non-zero integer modulo p, that is ZP. And Q is defined the subgroup, that is a collection of the elements in G. The A is quadratic residue. A is a quadratic residue. And the order of Q is p minus 1 by 2. That type of collection is order of Q is p minus 1 by 2. And Q belongs to Q, N is not belongs to Q, that is N is called the non-residue. Then NQ is a non-residue. Q is the residue, quadratic residue, N is non-residue, then NQ is the non-residue. If N1, N2 are non-residue, then N1 into N2 may be residue. That is the residue. So this is another, A is a quadratic residue of P, then A power P minus 1 by 2 equal to congruent to plus 1 modulo P. This is a maybe very important result. A is the quadratic residue of P, and A power P minus 1 by 2 congruent to plus 1 modulo P. And in an integer, in the integer modulo P, P is a prime number, there are at most n solution, there are at most n solution of x power n congruent to 1 mod p for every integer n. And non-zero integers modulo p under multiplication form a cyclic group. Non-zero integers modulo p under multiplication form a cyclic group if p is a prime. P is a prime. This is an example for the non-abelian group in which xy whole cube equal to x cube into y cube. That is the example, that is the group of 3 by 3 upper triangular matrices over Z3, over Z3 with ones on the diagonal. With ones on the diagonal, this is a collection. This is the Eisenberg group, that is the over Z3. It is a non-abelian, that is the xy cube equal to x cube y cube. The exponent 3, that is x power 3 equal to identity element, xy whole cube equal to is identity element, that is e into e, that is equal to x cube into y cube. So this group, but this group have the exponent 3. So that is x square, you can find it like that, x cube equal to identity element, that is these are modulo 3, that is 3 is congruent to 0 modulo 3, so therefore x cube equal to e for all x belongs to G. So G is a non-abelian group satisfying that xy whole cube equal to x cube y cube. So the same way G is a finite abelian group. The number of solution of x power n equal to e in G, where n divides order of G, then the number of solution of this equation is a multiple of n, En. And this is the, so all automorphism of S3 and S4 and the symmetric group of our degree 3 and 4, that is this is a symmetric group of degree 3 and 4. So 6 elements irukku. Its automorphism of S3 is isomorphic to S3 to itself, to S3 itself. That is the automorphism of S3. So every automorphism of S3 is inner and S3 has no outer automorphism. Inner automorphism, that is S3 no outer automorphism. So automorphism of S3 is isomorphic to S3. And S4 has 24 elements. So automorphism of S4 is isomorphic to S4. So S4 has outer automorphism. Actually, it is not a inner automorphism. So automorphism of S4 is isomorphic to S4. All automorphisms are inner. Therefore, this is because of S4 is complete. Therefore, automorphism of S4 is isomorphic to S4. So leave it. Okay. Stop here. Actually, soluble group la ungalku kedaiyadhu. Leave it. Any group of order p power n with p is a prime is nilpotent, must be nilpotent. Okay. Mostly syllabus இதெல்லாம் கவர் ஆகுதோ அதெல்லாம் நீங்கள் பார்க்கலாம். உங்களுடைய சிலபஸ் என்ன கவர் ஆகுதோ